In this video, we're going to begin to talk about infinite limits. So taking the limit of something as x goes to infinity or as x goes to negative infinity. Okay, so we're going to begin by doing this for polynomials and then for rational functions. So just for review, a polynomial is a function that has the form an times x to the n plus an minus 1 times x to the n minus 1 plus dot 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 plus a1 times x plus, and then the way we say a0 is we say a naught. So a0, we say a naught. So the word naught refers to the number 0. Okay, where the a naught, a1, comma dot 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 up to an are reals. They're just the coefficients. So we have some coefficient in front of x to the n, some coefficient in front of x to the n minus 1, all the way down until a naught would be the constant term. So a rational function is a polynomial, a function that can be written as a polynomial divided by a polynomial. So for example, e.g., something like f of x equals 2x minus 7 over x squared. That's considered a rational function because I have a polynomial on top of degree 1 and a polynomial on bottom of degree 2. So let's look at an example. First, we'll talk about how we take an infinite limit of a polynomial. So I have this infinite limit. X is approaching infinity of this polynomial. And what we want to do first is factor out the highest power of x. So doing that, we get the limit as x approaches infinity. So the highest power of x is x cubed. If we factor that out, we'll be left with minus 2, or negative 2. The next term we'd have minus 5 over x squared. Oh, whoops, I don't close the parentheses yet. And then from the 4, we'd end up with 4 over x cubed. So we could check this. If we were to distribute x cubed back into each of these terms, we'd get what we started with. So now we want to try to plug into this. So plugging in, we get infinity cubed times negative 2 minus 5 over infinity squared plus 4 over infinity cubed. In fact, let me put these other infinities in parentheses. Okay, so we have this. And now, what does this equal? So we have infinity cubed is a huge number cubed, which is going to be a really huge number. So that's infinity. And then negative 2 is going to be negative 2. And then when we have 5 over infinity squared, that's 5 over infinity. That's like saying we have $5, and we're going to divide that up amongst an infinite number of people. The more people that you divide that $5 among, the less each person gets. So 5 divided by a huge number is going to be really, really, really small, something really close to 0. So this fraction is approaching 0. So all right, there's that minus sign in front, minus 0. The next fraction similarly is approaching 0 as well, and there's a plus sign in front. So all right, plus 0. So overall, we have infinity times negative 2, which means it's negative infinity. And that's our answer. That's what the limit of this infinite polynomial is. So the key thing that I want to notice about this is, notice that the term that ultimately affected what the limit was this negative 2. The ones after that had these x's on the denominator. And as x went to infinity, all of those fractions became 0. And the negative 2 came from this term, the term of highest degree. So I want to notice that the highest power, which in this case is negative 2x cubed, dominates the growth. In fact, even if I had just ignored the other terms, ignored the minus 5x and the plus 4, we actually would have gotten the exact same limit. So that's true in general when we have polynomials. And also, as we'll see when we talk about rational functions right after this. Okay, so we did that example. Now let's talk about rational functions. So when we have an infinite limit, let's just say x is approaching infinity, but it also could be approaching negative infinity, of r of x, where r of x is rational function. Now we are going to factor out the highest power of power of x from the numerator and the denominator. From the numerator and the denominator. And after we do that, then use logic. Use logic as we did in this example. All right, so let's look at an example. So example 9, evaluate the following limits. In part A, I have the limit as x is approaching negative infinity this time, and then I have this rational function, polynomial divided by a polynomial. So let's remember that our first step in doing limits up until this point has been to plug in. And I know I didn't plug in into the last example, but that's okay. We were actually able to evaluate it even without plugging in. But let's just plug into this to see what we would get. Now that we know that the highest power term sort of dominates the growth when x is going to infinity or when x is going to negative infinity, let's just focus in on those highest power terms. So it's negative 4x squared on the top is the highest power term. On the bottom, it's 2x. So if we were to just sort of plug into those, on the numerator, we'd get negative 4 times negative infinity squared. We'd get negative 4 times negative infinity squared. On the denominator, we'd get 2 times negative infinity. So overall, the numerator gives me negative infinity. The denominator gives me negative infinity. And this is an example of one of our indeterminate forms. And when we have an indeterminate form, our strategy has been to simplify. To simplify first before we plug in. All right, so that's why I'm going to try this factor out the highest power of x that seemed to work well with polynomials. Let's see if it works well with these rational functions. So the highest power of x on the numerator is x squared. Factoring that out, I'll be left with 3 over x from the first term, minus 4 from the next term. And then from the 7, we'll have plus 7 over x squared. On the denominator, the highest power of x is just x. And then factoring that out, I'll be left with 2 plus 5 over x. Okay, so now I can cancel a little bit. I have the limit as x approaches negative infinity. And the x squared and the x will cancel. I can cancel one of those x's, and I'll be left with just x on the top. So I have x times 3 over x minus 4 plus 7 over x squared over 2 plus 5 over x. Whoops, plus 5 over x. Now, let's try plugging in. So if we plug into this, plug in negative infinity this time into the x, we'll get negative infinity out in front. And then we'll get 3 over negative infinity minus 4 plus 7 over negative infinity squared. And then all over 2 plus 5 over negative infinity. All right. So what we have now is we have this negative infinity in front of the parentheses on top. So a bunch of these terms are just going to approach 0. So having 3 over a huge number, even though it's negative, means this is going to get really, really close to 0. Same thing with having 7 over negative infinity squared. It's going to get super close to 0. And same thing with this one. 5 over negative infinity, that's going to get close to 0. So on the top, in the parentheses, we are left with just negative 4. On the denominator, we get 2 plus 0, which is just 2. So overall, we have the double negative cancels, and we'll end up with infinity times, and then 4 divided by 2, we get 2. 2 times infinity is even bigger, so this is infinity, positive infinity, in fact. And that's our answer. That's what this limit is. This limit ended up being positive infinity. All right. So eventually we'll talk about a shortcut for doing limits like this, these infinite limits of rational functions. But for the time being, I'm going to do it as it is, by doing this factoring technique. So let's do some more examples. So some more examples. So this is going to be part B of this. So now I'm going to have a limit as x goes to positive infinity. and a slightly different function. I have the same polynomial on top, but on the bottom I have something different. So let's begin by distributing at the bottom so I can see what the highest power of x is. So foiling this out, I'll get 16x squared. That's the 2x times the 8x. 5 times 8x is 40x. So 40x. And then 2x times negative 1, it will be minus 2x. So 40x minus 2x, that is plus 38x. And then finally, 5 times the negative 1 is minus 5. So again, let's factor out the highest power of x in the numerator and denominator, which is x squared for both of them. So on the top, I'll be left with 3 over x minus 4 plus 7 over x squared when I factor out that x squared. On the denominator, if we factor out x squared, we'll be left with 16 from the first term plus 38 over x from the second term and minus 5 over x squared from the third term. At this point, we are ready to plug in. And when we plug in infinity, oh, actually, I can cancel something first. The x squared here and the x squared there, they've been factored out, so they cancel out. Okay. And now when I plug in infinity into this, a bunch of these terms are going to get close to 0. In fact, any of these terms that are, so like the 3 over infinity is going to get close to 0. Same thing with the 7 over x squared, it's going to get close to 0. On the numerator, what I'll be left with is negative 4. On the denominator, what I'll be left with is 16. In fact, let me just write it out so I can see everything that goes to 0. So the 3 over x will go to 0, and then I have minus 4. 7 over x squared is also going to go to 0, because I end up with 7 over a huge number, which is really, really close to 0. On the denominator, we have 16, and then 38 over a huge number gets really close to 0. And then minus 5 over a huge number gets close to 0 as well. So the minus sign, I'll just write minus and then 0. So we end up with negative 4 over 16, which is negative 1/4. And that's our limit. Okay, so it's just negative 1/4. So let's do one more of these. Okay, so let's do the limit as x approaches infinity of this rational function now. So before I do this, just quick comments about this, the previous examples. So in part A, we saw an infinite limit of a rational function that ended up being positive infinity. So this indeterminate form, this infinity over infinity type indeterminate form, could give me infinity, like we saw here. In part B, both the top and the bottom are going to be some type of infinity, either positive or negative, if we were to just plug into them. But that indeterminate form could be a finite number, like negative 1/4. So that's interesting. And then now let's do one more example. So part C. So let's do the same thing. Let's factor out the highest power of x on the numerator and on the denominator. So on the numerator, it's x squared, and we've done the numerator a few times now. Let's do it quickly. So 3 over x minus 4 plus 7 over x squared. On the denominator, the highest power of x is x to the 5. If we factor that out, from the first term, we'll be left with 2. From the next term, we'll have a minus 8, and we would need to put an x to the 4 in the denominator, so that when I distribute the x to the 5 back, we'd end up with just minus 8x. So I can cancel a little bit. I can cancel 2 of these x's with 2 of these x's, but be left with x cubed in the denominator. And now when I plug in to the numerator, 3 over infinity, that's going to be 0. I have minus 4. 7 over infinity squared is 0. On the denominator, we have x cubed, so that'll be infinity cubed times 2 minus, and then 8 over infinity to the 4th, that's 0. So overall, we have negative 4 on the top. On the denominator, we will have infinity, because that's what infinity cubed is, it's infinity, times 2. So 2 times infinity is infinity still. So negative 4 over infinity is 0. All right, so now we've seen that a limit of the form, this one's also going to be of the form infinity over infinity, maybe with the negatives. But an indeterminate form like that can also be 0. So in the next video, we will learn a shortcut for finding infinite limits of rational functions.